Hi everyone, today I'm going to introduce you the paper Content Extraction via Tag Ratio written by Tim Weininger, William H. Su, and Jiawei Han. So this term can be abbreviated as CETR and pronounced as cedar as in cedarwood. So first, this is the content table with all the topics that I'll expand on. I'll go over introduction to the topic, some related work and application, and then I will explain CETR, cedar, in their one-dimensional model and two-dimensional model. And then the authors done some experiment on the cedar methods. And also I'll go over pros and cons for this paper. So all of us are realizing the rapid increase in the amount and also the type of data these days. The demands for gathering and processing such data also increases, as the data can be translated into insightful messages that are crucial for various aspects in our lives. So content extraction come into play. Furthermore, massive non-content text and images are interfering with the extraction and slowing down the speed of getting more important content. So we want to develop the algorithms frequently to adapt to this situation. And that's why we should care about this topic. Interestingly, tag ratio method was mentioned in our week 5 lecture as one of the structural analysis approach. And we are also working on assignment 1 now. So I guess all of you have realized the power of scraping method, extracting words from website that allow us to obtain the information we want. Before I dive into details of content extraction via tag ratios, I would like to briefly introduce some previous related work. So at the beginning, the approach for extracting content would just be creating web scrapers for certain websites. And since it's kind of the simplest approach, its limitation is also apparent, such that when you switch from one website to another for a new scraping task, you usually need to modify the rules because they're just different websites. Even when you establish the rule for a certain website, it can also happen that the maintainer of the website changes the structure, so then you have to start over again. Then there comes many new algorithms that can be applied more widely, so not limiting to a single website. An example would be body text extraction, BTE. And as you can tell from the name, the algorithm would be to identify a single chunk that contains the most words and the least amount of HTML tags. There's also content code blurring, which is the method most similar to cedar, that identify content regions by searching for source code character sequences that are formatted homogeneously. And for some other methods, I'm not going into details for each one as the main focus is cedar here, but it's worth giving credits for them as they built the foundation of this research, and they were also tested for efficiency along with cedar in the experiment that I'm going to introduce later. For the applications, you're actually experiencing content extraction every day. For example, when you're using web browser on your phone, content extraction is helping the website adapt to the much smaller screen compared to the larger computer screen. And there's also an application of RSS, the really simple syndication. Whenever an RSS feed is published, you can directly receive updated information without manually checking for it. Then information retrieval benefits from content extraction as well, as the most relevant information will be returned based on the keywords you put in during searches. Now, many of the methods I mentioned before have shown some disadvantages, such as requiring training, being time-consuming, being inaccurate, and the biggest shortcoming is as the styles of the website are continuously evolving, these methods are being less applicable. So using this website, for example, we can see that there are many irrelevant advertisement sections that can interfere with the process of extraction. And the only part we care about is in this green box. Now, therefore, the authors are realizing there's a need to find a new method that's more general, more adaptive to the current web structure. And that is what led the authors develop this cedar method. So the first step is simply computing the tag ratio for each line in the HTML document. The algorithm is shown here on the left. So the input would be the document and the output will be a histogram by putting all the tag ratios together. And then the script, remark, and style tags shown here are removed because the text in those tags can skew the result. And for the actual calculation, we have the number of non-tag characters as X, the number of tags as Y, and the ratio would just be X over Y. Now it can happen that the number of tags is 0, and we can see for the fourth line on the example on the right, we know that 0 cannot be the denominator. So in order to make division work, we're assigning 1 to the number of tags. So in this example, the tag ratio is 37 over 1 instead of 37 over 0. Now to the second step, with all the tag ratios, a histogram is generated. We can see that around 220 to 260, the tag ratios are higher. So it might indicate these lines correspond to the content of the website. Then the authors took into account that some of the important tags, such as the title, can have a small tag ratio that can make themselves being recognized as non-content part. So they applied a Gaussian smoothing, modify it to a more suitable function, and generated a smooth histogram shown on the right. And we can see the boundaries between sections become more apparent now. Now with this smooth histogram, the authors developed two ways of analyzing it. The first is called Cedar TM, which is a threshold method. So with the threshold tau, lines with a tag ratio above the threshold will be classified as content, and those lines with a tag ratio below the threshold will be considered as non-content. And the other method is called Cedar KM, which is a k-means clustering method. The number of clusters k will be z, and the clusters having the centroid closest to the origin is identified as non-content, and the rest is identified as content. Now with both methods, the content line will eventually be combined and exported to a file for future analysis. But both methods are used for like one-dimensional model, and the authors realized that they have a disadvantage when there are jumps in tag ratio data. So it's as important as jumps can usually identify where content sections start and end. Therefore, a two-dimensional model was built by creating an additional absolute smooth derivatives of the smooth histogram. And it's done by a set of computations, transformations of the data. And the final histogram is shown here on the right. So the first spike represents the start of the content section, and the second spike represents the end. And after that, a k-means clustering method is applied again, but this time there's a slight modification, such that one of the centroids is forced to be at the origin so that the corresponding cluster can be identified as non-content, and the other clusters are considered content. So with the final version of Cedar confirmed, the authors move on to testing the three methods, along with the previous method they want to compare all the methods to find out if the Cedar algorithm can meet the expectation of having the best performance. So they collected website documents from various sources, and they also chose some Chinese documents to see if Cedar can function well on different languages. And all of the documents were from some researches or projects. So the beginning and end of content section were already labeled by those researchers and like project participants. And that will allow the authors to calculate the precision, recall, and F1 scores for all the methods. So for the result, they first found that Cedar performs much better than Cedar KM and Cedar TM. And they're aware that Cedar doesn't treat comments as content. So for some websites that accept comments, Cedar can, in theory, perform better if the comments are turned off. And in addition, for the Cedar TM approach, remember the threshold tau equals lambda sigma. The sigma is the standard deviation of the data, and the lambda can actually be tuned by users themselves so that the threshold can be adjusted. If the lambda increases, threshold tau increases, and precision can be increased. But you cannot have high precision and high recall at the same time, so it's totally up to the users to balance between the two. Then for the result of comparing all the methods in parallel, we can see that the bolded ones are winners. So, and the Cedar has the most bolded data here on the last line. So it was concluded that Cedar demonstrated its strength over other methods by having a simple algorithm and the highest effectiveness in content extraction. So for some pros and cons of this paper, overall, the paper is really organized. It has sections labeled that summarize what the sections are about. And the paper explained tag ratio algorithm by applying to a real example. So the algorithm is no longer just a theory, but something we can see. And there are also figures and equations that aided in the explanation of the 1D, 2D modeling part. And also the authors share their motivation of running this research by connecting the previous content extraction method to the evolving website structures. But at the same time, I also have some concerns about the paper, such that there's a lack of explanations for some statistics and machine learning terms, such as the Gaussian smoothing, k-means clustering. So the readers with no such domain knowledge may find it hard to follow. Then the authors were also aware that their clustering method was actually not the optimal one. So this may raise concerns such that what if they use the optimal clustering method, would CEDAR still perform well? And this paper was written in 2010, so it's been over 10 years. And there seems to be a necessity for future works on this topic. And that's all I want to share. And thank you so much for watching.